Here if one of these integers I and j is less than 2, okay, that is if one of them is 1, okay, since I and j are distinct, okay, I mean, if you consider, okay, so from this argument it follows that a transposition ij with I and j both at least 2, okay, and with I and j being distinct, that can be expressed as product of transpositions of this from 1 up to, I mean 1, 2, 1, 3, 1, 4 till 1n. Sorry, the last one just went beyond the margin. and if you take a transposition I comma j where one of them is at least 1, then you already have them here, okay. So thus from this argument we have seen that any transposition can be expressed as product of all of them, and from this corollary we knew that any permutation can be expressed as product of transpositions, okay. So we have just established that any permutation in Sn can be expressed as a product of the transpositions of the form 1, 2, 1, 3 till 1n. Okay, so for instance, if you are given this transposition I comma j, we can write it in this form, okay. Great. Yeah, and just few more notations to introduce, or notions. So if you start with a subset, we have already seen the notion of generating, or at least we have already seen the notion of generator of a group, okay. Here we will do things in bit more generality, where we will start with a group and a subset S of G. Then the subgroup of G generated by S, the subgroup of G generated by S is denoted by S within this, what do you call this, angle brackets. And then this is defined to be the smallest subgroup of G containing S, okay. There will be several subgroups of G that contains S. So to start with, you will have G itself, and there will be few others, or there might be none, okay. So you look at the smallest among all of them. Indeed, if you write down, I mean, if you take all the subgroups of G, that is if you consider the collection of that is if you consider the collection of subgroups of this group G that contain S, then their intersection will precisely be this subgroup of G generated by S, okay. So let me first indicate that if you take a collection of subgroups of G, okay, then the intersection of this collection, that is again a subgroup. This is something that you have seen in the specific instance of intersection of two subgroups for sure, and by the same argument it also follows that the intersection of collection of subgroups is also a subgroup of G. And now if you to understand this smallest subgroup of G containing S, you look at the subgroups of G that contain S and look at their intersection. That turns out to be that is definitely the smallest subgroup of G containing S, because that being the intersection, since you are looking at the intersection that is contained inside any subgroup of G that contain S, okay, as a subset. Okay, great. So the smallest subgroup of G generated, containing S, which is denoted by S within angle brackets. So that is equal to the intersection of the subgroups of G containing S, okay. If you want, you can take this as the definition also. That is also fine, okay. Great. And if you for a subset S of a group G, we say that S is a generating set of this group G when the smallest subgroup of G containing S, that is this one, okay, if that is equal to the full group G itself. Okay, that is G does not have any subgroup other than G that contains S as a that contains S as a subset, okay. Here's a quick exercise for you, which says that if you have a subset S of a group G, okay, then that is a generating set of G if and only if any element of G can be expressed as a product of the elements of S and the inverses of the elements of S, okay. So this is not too difficult. This is just about unwinding the definition that we have learned, okay, in this bunch of lines, okay. Just let me make a few remarks. This is a follow-up remark of what you have just discussed. Here you have seen that any permutation in Sn can be expressed as a product of these transpositions, right? So in fact we have shown that this set consisting of 1, 2, 1, 3 till 1n, so this set is a generating set of Sn for any n at least 2, okay. And so now we'll learn an important property of transpositions, okay. So if you have an element psi of this permutation group Sn, and suppose psi can be expressed as sigma 1, sigma 2, sigma r, and psi can also be expressed as tau 1, tau 2, tau s, where the sigma i's and tau i's, they are all transpositions. So So you're expressing psi, a given element of this permutation group Sn, as a product of transpositions, okay, in two different ways, in this form first and then in this form first, okay. Then what can you say? Can you say that sigma 1 up to sigma r, they're equal to tau 1 up to tau s in some order? All that questions, I mean, all these questions are very natural to ask, okay. So it turns out that what one can say is that R and S, they both have the same parity. That is, both of them are either odd or both of them are even. Okay. Yeah. So if you have if you express a permutation as a product of transpositions in two different ways, then one can say that the number of transpositions in both the expressions, that is R and S, they have to have the same parity. This is a result that will not complete. I mean, will not present a complete proof of this theorem in this lecture. We'll just leave some of the important one of the important step or the crux of this proof for the upcoming lecture. So we have sigma 1 up to sigma r equal to tau 1 up to tau s. That is, the identity permutation can be expressed as in this fashion, and the inverse of tau 1 up to tau s is equal to tau s inverse till tau 1 inverse, and this tau i's being transpositions, that is permutations of order being transpositions, their elements of order 2, okay. That is that shows that this identity element can be expressed as the product of transpositions in this fashion, okay. Now if you could show that the number of transpositions here, which is r plus s, if you could show that the number of transpositions here is an even number, okay, then you are done. So you have expressed the identity element as a product of transpositions, okay. If you could show that the number of transpositions that you have used, the number of transpositions, the number of the transpositions that have been used here, if the number r plus s is an even number, then you will be done. Then r and s will have the same parity, okay. If you could show that r plus s is even, then it will follow that both of them are either odd or both of them are even, okay. And this is something that we will do in the next lemma, which says that if the identity element of the permutation group Sn can be expressed as product of transpositions. So here please do not get confused between this choices of sigma i's and this sigma i's, okay. These two are, the sigma i's have been used in these two different contexts in a different manner, okay. The idea is, so this lemma summarizes, states that if identity element can be expressed as product of transpositions, okay, product of R transposition, then R has to be even. The sigma i's doesn't have anything to do with this sigma i's, okay. Anyway, we'll postpone the proof of this lemma to the next lecture, okay. It's not too difficult though, but you can try to think about it. But we'll definitely discuss this lemma in the next lecture. But for a while, we'll accept this lemma and we'll try to move on. So applying this lemma, this proof is complete, okay. This the proof of this theorem that here R and S, they have to have the same parity, that is both of them are either odd or both of them are even. Okay, great. And an immediate implication of this theorem is that if you try to express a permutation sigma of Sn, okay, an element psi of Sn as a product of transpositions, okay, then either you will be able to express it as a product of even number of transpositions or odd number of transpositions, okay. Because if you have already expressed as an even number of transpositions, then no matter how you try to express as product of transpositions in any other way, that integer s have to have the same parity as that of r. So s has to be even, and if r is odd, then s has to be odd, okay. So you have this immediate corollary that any element of Sn can be expressed either as a product of an even number of transpositions or as a product of an odd number of transpositions, okay. And certainly an element of Sn, I mean that can be seen by taking few elementary examples, that a specific element of Sn may have several decompositions into transpositions, okay. So though these expressions are not unique, but the number of transpositions involved, that is their parity is unique, okay. So for instance, this the cycle inside this permutation group S8 can be expressed as 1 3 times 1 2. This can also be expressed as 1 3 times 1 2 times maybe 6 7 5 6 6 7 5 7. If you want, you can add maybe more elements or maybe not, because I think I've used essentially all that I could have. No, there is still some space. You could write 4 8 here, or maybe, and you can also include 4 8 here. I hope 4 and 8 are not used here. Yeah, so they are disjoint cycles, so this is fine. Okay, and from this corollary, we can okay, from this corollary, after discussing this corollary, you can move on to this definition, and this corollary justifies, or corollary indicates that this definition makes sense. Okay, we are going to define this notion of an even permutation and odd permutation. This says the following: if you have an element of Sn that is called an even permutation, if it can be expressed as a product of an even number of permutations, and it's said to be an odd permutation if it can be expressed as a product of an odd number of transpositions. And just because we have seen that the number of transpositions that is required to express as that is required to express a given element of Sn, that is required to express the given element of Sn as a product of them. Okay, that number R need not be unique, but the parity is unique. So this shows that this definition makes sense. Okay, with this we stop here, and yeah, in the next lecture we need to need to discuss the proof of this lemma 251, that the identity element of Sn, if it is expressed as a product of transpositions, then the number of transpositions has to be even. Okay, great. Then we stop here.